Transformations of functions. In this section, we look at how to get the graph of a function from a known function by looking at transformations. The first type of transformation is what is called a vertical shift of the graph. So if we know the graph of some function, adding a constant to that function will shift the graph up or down depending on whether that number is positive or negative. So if we have a function f of x and we add a positive number c, it is going to shift the graph upward c units. If we subtract a number c, it's going to shift the graph downward c units. So as an example, suppose we are looking at the graph of f of x equals x squared, which we know is this parabola right here. What is the graph of x squared plus 3 going to look like? Well, it will be the same graph, but shifted up 3 units. And you can see that is the red graph here. Likewise, the graph of x squared minus 2 is going to be this graph, but shifted down 2 units. And that is this purple graph that you see here. So if we know what the graph of x squared looks like, we can very quickly and easily get the graphs of these two functions by simply doing a vertical shift. Graphs can also be shifted horizontally. So to shift a graph horizontally, a distance of c units either to the right or to the left, we have to either subtract c or add c to x inside the function. So this is very different from what we did just a minute ago. Let's take a look at an example. So in this example here, we have once again the same function, f of x equals x squared. But now I'm looking at a new function, x plus 4 quantity squared. So the 4 is being added to the x before we square it, right? So instead of adding 4 outside the function, we're adding 4 to x inside the function. And this is going to shift the graph 4 units to the left, okay, to the left. And so x plus 4 quantity squared is going to be this graph here. So notice that that is just the basic graph x squared, but shifted to the left 4 units. The other function, x minus 2 quantity squared, is going to be this graph shifted to the right 2 units. We can also combine horizontal and vertical shifts. So for example, suppose I want to sketch the graph of the function f of x equals the square root of x minus 3 plus 4. First thing I need to do is consider what does the function f of x equals the square root of x look like. So this is one of those functions that we should kind of have memorized. We should know that the square root function looks something like this. And you can actually see that down here. That is the purple graph. So this is kind of like our beginning function. Now the square root of x minus 3 plus 4 involves a shift of 3 units to the right and 4 units up. So if we take this graph and shift it 3 units to the right, we get this graph. And then if we take that graph and shift it 4 units upward, we get this graph here. So this is the graph of the square root of x minus 3 plus 4. Graphs can also be reflected over the x-axis or the y-axis. To reflect a graph over the x-axis means to simply do a mirror image of the graph where the x-axis is the mirror. And to do this, we simply take the opposite of f of x. So we literally just put a negative in front of the function. To shift a graph over the y-axis, we put a negative in front of the x variable. Let's take a look at an example. Suppose we want to graph each of the following functions. So in part A, we have f of x equals negative x squared. So we know that x squared is the parabola that you see here. So we have just put a negative in front of that function. That is going to shift this graph, it's going to reflect this graph over the x-axis. So negative x squared is simply this red graph that you see here. For part B, we want to graph the square root of negative x. Well, we know that the square root of x is this graph. And now notice that the negative is on the inside of the function as opposed to the outside. So this is going to shift it over the y-axis. So if we do a mirror image of this graph over the y-axis, we get this graph here. Graphs can also be stretched or shrunk vertically. To stretch a graph, what we do is we multiply the function by a constant c that is bigger than 1. And to shrink a graph, we multiply the function by a constant c which is in between 0 and 1. So for example, if this blue graph is our function, multiplying it by a number c that is larger than 1 is going to essentially make the graph taller. If we have our function and we multiply it by a number c which is between 0 and 1, it is going to make the graph shorter, right? So notice that the red graph here is shorter than the original function, and the red graph over here is taller than the original function. So for example, going back to our function f of x equals x squared, which is our basic parabola here, the graph of 3x squared is going to be taller. And so that is this red graph right here. Now, how much taller is it going to be? Well, notice that the point 1, 1 is on your original graph. And on your new graph, you have the point 1, 3, which is right there. The point 1, 3 is 3 times as tall as the point 1, 1. And the reason it's 3 times as tall is because we multiplied x squared by 3. Likewise, the graph of 1/3 x squared is going to be a graph that is 1/3 as tall as the original graph. So if you look at x equals 1 down here, you can see that this y value is 1/3 as tall as the original y value. And so that in essence makes the graph shorter or wider. Now we can combine all of these together and we can sketch a graph of a more complicated function such as the one that you see here. So to sketch a graph of 1 minus 2 times the quantity x minus 3 squared, it's best to do this in steps. So first we start with the graph of the function x squared. Now what I'm going to do is go to my function here, go to the x, and ask what's the first thing that happens to x? So if you plug in a number, what's the first thing you would do to that number? Well, the answer is you would subtract 3 from it. So the first thing that's going to happen is you're going to subtract 3 from x and then square it. Now what does that graph look like? Well, this is going to be a graph that is shifted 3 units to the right. And so you can see that is represented by this purple graph right here. What's the next thing that happens? Well, the next thing that happens is we're going to multiply that by negative 2. So the next function is negative 2 times x minus 3 squared. Now this does 2 things. The negative is going to reflect over the x-axis, and the 2 is going to stretch the graph to be twice as tall. So if you take the graph of x minus 3 squared and you reflect it over the x-axis and make it twice as tall, you get this blue graph down here. Now the last thing that happens is the 1 here. And so in essence, what we're doing here is we're just adding 1 to that previous equation. Now, that is the same as putting the 1 in front of the -2 here. But all we're doing here is we're moving the graph up 1 unit. So if you look at this blue graph here, if you shift that graph up 1 unit, you get this red graph. And so the red graph is the graph of this function. Graphs can also be stretched and shrunk horizontally. To do this, we're going to multiply x by a number c. And you have to be a little bit careful because when c is bigger than 1, it's actually going to shrink the graph by a factor of 1 over c. And if c is a number in between 0 and 1, it's going to stretch the graph by a factor of 1 over c. Let's take a look at an example. Suppose we have some function, which is often called a sawtooth function, that you see right here. And you can see that each tooth of this saw is 1 unit tall, and it lasts for a distance of 1 unit. So what would happen to this graph if we did f of 2x? So again, we're multiplying x by 2. 2 is a number bigger than 1, and so this is going to shrink the graph horizontally by a factor of 1 over 2. So the result is you're going to get a sawtooth where each tooth of that saw is now happening in a distance of 1/2 instead of a distance of 1. And for the second one here, f of 1/2 x, we're multiplying x by a number less than 1. This is going to stretch the graph by a factor of 1 over c, which is 1 over 1/2, which is equal to 2. So if you look down here, this is a graph of f of 1/2 x. What we've done is we've taken this sawtooth, which used to last a distance of 1 unit, and now it lasts a distance of 2 units. So you should see that this graph here has been horizontally stretched, whereas this graph has been horizontally compressed or shrunk. And lastly, let's talk about even and odd functions. So an even function is a function that has symmetry across the y-axis, and an odd function is a function that has symmetry through the origin. The way you test for it is by plugging -x into the original function. So a function f is even if f of -x is the same as f of x, and a function is odd if f of -x is the opposite of f of x. So the most classic example of even and odd functions would be the functions f of x equals x squared, which is an example of an even function, and f of x equals x cubed, which is an example of an odd function. Now, why is x squared an even function? Well, simply put, we can see that it's even because it has symmetry across the y-axis. But also, if you do f of -x for x squared, this is going to be -x quantity squared. And we know that -x quantity squared is the same as x squared, which is the same as the original function. So that is why this is an even function from an algebraic perspective. F of x equals x cubed is an odd function. Why? Because if I take a point up here, we can see that it has symmetry through the origin on the other side. Now we can also test for this by once again just plugging -x into the function x cubed. When we do that, we get -x quantity cubed. And when you remove the parentheses here, you get -x times -x times -x, which is negative x cubed. And this is negative f of x, right? Because it's the opposite of the original function. And because of that, that is why it is an odd function. Now, of course, the names even and odd pretty much come from these two examples. Notice that the power here is even and the power here is odd. But you have to be careful when you look at powers because powers don't always tell the full story. Let's do one last example. So here we want to determine whether each of the following functions are even, odd, or neither. So let's go ahead and look at the first function, f of x equals x to the fifth plus x. To test to see if this function is even or odd, we're going to plug in negative x. When I plug in negative x, replacing x, we get the following. Negative x, quantity to the fifth power, is the same as negative x to the fifth. And when you add negative x, you just get minus x. And I want you to notice that if you factor out a negative here, you will get x to the fifth plus x. Do you notice that this is our original function? Right? That's what we started with. So this is equal to negative f of x. And so this first function is odd. For the next function, we have g of x is equal to 1 minus x to the fourth. To test to see whether it is odd or even or neither, we are once again going to plug negative x in place of x. So when you do that, this is what you get. Now you have to be very careful here because it's very tempting to want to cancel these negatives. But remember, this fourth power applies to this negative before this negative does. So when you raise negative x to the fourth power, you actually get positive x to the fourth. However, there's still a negative right here. So this negative comes down, this negative goes away. And what you should notice is that this is exactly the same as your original function. So this is equal to g of x. And so that means g of x is an even function. And finally, for h of x, to see whether it is even or odd or neither, we are once again going to do the same thing. We're going to plug negative x in for x. This is going to give us 2 times negative x minus negative x quantity squared. 2 times negative x is negative 2x. This negative here comes down, and negative x quantity squared is x squared. Now I want you to notice that this is not the same as the original function, so it's definitely not even. And if you factor out a negative, you get 2x plus x squared left over. And notice that this is also not the same as the original function. So you don't get h of x, and you don't get the opposite of h of x. And so this function is neither even nor odd. And that concludes this video lesson.